Hello, everybody. Let's do a quick introduction to 3D vectors. So, two-dimensional vectors have two components, x and y, that describe how far over and how far up. Just as a note, I'm going to be treating all of these as position vectors. So, if you want to do a three-dimensional vector, let's just add a third component. It doesn't make sense to refer to over anymore, because x is going over and y is also going over, in a certain sense. So you could refer to, like, east, west, north, south, up, down could be what we do, or probably I'll just say in the x direction, in the y direction, or the z direction. Any way you talk about it, those are the three separate directions that are our three dimensions. It's a little... All right, so let me try and do my best to plot it. So 2 in the x direction would be here. 1 in the y direction would be here. So that dot is supposed to be in the xy plane here, so it's got no up or down component. But now if I'm going to go up by 3, I want to go straight up from that point, 1, 2, 3, so kind of here-ish. So this would be the point 2, 1, 3. All right, because this is really hard for me to sketch in 3 dimensions, and Desmos just has created a new 3-dimensional capability, let's jump on over to Desmos. I would definitely encourage you to do this also. You can get there by saying desmos.com/3D. All right, so remember in Desmos you can't use triangle brackets, you have to use parentheses. But here's 2, 1, 3. And you can drag and sort of move around, and you'll see the X and the Y and the Z. If you hit this button right here, XY orientation, it will move it so that you're looking straight down from the top. And so here you can see that the x-coordinate is 2 and the y-coordinate is 1, just as desired. And now if I click and drag, so you got to remember the x-coordinate is 2 here, because that's going to disappear. So here x-coordinate is still 2, and you can see that the z-coordinate is 2 and another one 3. So a really helpful thing to do, once we're going to have more complicated equations, is to look at the projections. What a projection means is you're just going to be looking down on two axes, so either xy or xz, or over here is yz. So it's nice to look in 3 dimensions, but sometimes it's very instructive to just look in the 2 dimensions. Okay, so let's get from here to equations. All right, so let's start with y equals sine of 2 pi x. So if I was graphing x versus y, that would look, you know, like that-ish. What if I want that same equation to appear in the xy plane here? So it'll look, you know, something like this, all in the xy plane. So let's think about what the x, y, and z are going to be. Clearly, because no point on this curve is going up or down at all, we can have the z component be 0. X and y are both going to be described in terms of time. So here, let's say that we're going to be moving in the x direction just the same as t. How will we calculate our y-coordinate? Well, if x is just the same as t, then that means that y is going to be that function of t, sine 2 pi of t. So here we'll do sine 2 pi t. Let's go ahead and look at it in Desmos for a minute. So I'm going to remove that point. So we said the x-coordinate is just t, the y-coordinate is going to be sine 2 pi t, and the z-coordinate is going to be 0. So you can see there's exactly one sine wave, and if I go to the xy plane, you can see it being graphed. The reason it's only doing 1 is because my time interval is going from 0 to 1, but I could make it like 0 to 6, and now we're going to continue to graph it for larger intervals of t. So you can sort of like drag it around a little bit. As an exercise, why don't you imagine how could we have this same graph except going up the z-axis instead? So it's going to be oscillating around y, and the z is moving up. Go ahead and experiment a little bit, see if you can get that to go. Okay, in this case, no point along this curve has an x-coordinate that's different from 0, because this entire curve is supposed to be in the yz plane. So for my x component, it's just 0 all the time. My y component is the one that's oscillating. So here we're going to keep sine 2 pi t is the y component. And then the z component is it's sort of like the independent variable. It's the thing that is going to cause, it's the thing whose change is going to cause the oscillation. So you can imagine this as time increases, our z-coordinate is increasing at a constant rate, and then the y-coordinate is the thing that's oscillating. Okay, let's look at it in Desmos. So here we are. I'm going to make this be 0, whoops, and this be t. And now you can see, if I'm looking at it in the xz plane, or in the yz plane, you can see the oscillations. Here, if I'm looking at it in the xz plane, it doesn't look like anything, because the entire curve is in the yz plane. Okay, let's start to make some other examples. So go ahead along with me and let's make the curve be back in the xy plane. How would I shift this entire curve up a little bit? Hopefully you think, oh, well, I'll just set the z-coordinate to be like 2. And so now I've shifted the whole thing up, so the z-coordinate's always at 2. Imagine what would happen for a second if we replaced the z-coordinate with t. So in other words, as the x-coordinate is increasing, the y-coordinate is also increasing at the same rate. Try and imagine it for a minute. And now let's look. So you can see that the oscillation is happening along this kind of diagonal line. In fact, if we look at the xz plane, you can see the diagonal line that it's of the plane that it's oscillating inside of. So if I look at it this way, you can see the oscillations. If I look at it sort of straight on, like diagonally, here-ish, that's what it looks like. So let's try and put a straight line that goes like right through the middle of the oscillations. If I think about what my straight line needs to look like, the y-coordinate is always 0 because I want to go straight through the middle of the oscillations. And it looks like whatever the x value is, that's also what the z value should be, because I want it to go sort of at a 45-degree angle along this xz plane. So let's put it all together. I said whatever my x-coordinate is, that's the same thing as my z-coordinate. And my y-coordinate is 0. Let's get rid of this terrible color. Let's make it green. Right now, you can see that the time interval just goes up to 1, but it does seem to be going kind of down that diagonal. I can set the time interval up to 6, and now I'm going straight down the middle there. So, what are some helpful thinking tools here? Some helpful thinking tools are imagining what x, y, and z are doing separately, and you can help visualize it by looking along different projections. Here I've modified the equation to have circular motion, so you can see in the, let's make this be 10 and 10. You can see that in the xy plane I have cosine sine, so that's creating this circle in the xy plane. I've left this diagonal line along the xz plane there. I just wanted to point out you can also imagine these like vectors. Well, let's not do that yet. Let's actually look at it like an animation. So if you're using lowercase t, it will plot all of the points in the interval when t is between two numbers. If I make a copy of this and then I replace it with some other variable, such as capital T, you can add a slider. I want to change the interval here to match the interval of my path. But now, as you drag the slider, you can actually see the movement. So you can see this rotation there. You can also think about these as vectors. So here I have two separate, well, let's look at this one. I'm going to replace these with capital T. Okay, so now when I press play, you see two different movements. This equation is a circular movement. This equation is a linear movement along the diagonal line, except I think I want it to go a little slower, so I'm going to divide by 3. Let's see how that looks. Okay, that's pretty good. Okay, remember, vectors are a great way of combining simple movements to make a complex movement. So in Desmos, you can actually just add together these two as if they are vectors. So I'm going to cut this, I'm going to say plus, and I'm going to paste. So now I have a new vector that's the vector sum of the rotation and the translation. And here's what it looks like. It's a little hard to visualize with just the moving point. Let's look at it in this axis. So you can see it sort of orbiting this line. So let's not just have this one. Let's also put in the lowercase t's here. So now we can visualize the path that it's taking, which is really, really cool. It's not quite a circle around this diagonal line, because the rotations are still happening in the xy plane. It's just that as the xy plane is rotating, there's a constant increase in the z. But anyway, hopefully you're starting to get a sense for the power of both the thinking tools for parametrics and vectors, and also for this great computational tool of Desmos. I think a great thing to do now would be a couple of exercises where you try and have circular motion in different axes. You experiment with scaling, and you experiment with translation. Hope this was helpful.